Okay, so for this demo of life cycle assessment in practice, we're going to model a small studio building, studio residence in eTool lifecycle design software. So I've created a blank design here, and we're going to use the Revit plugin to push some BIM information from the model into eTool LCD. So there's a plugin for eTool. I've got my really basic model here. We've located this building in Western Australia, which is where I'm doing this demo. And we've sort of chosen some business as usual components for this. It's in a slightly colder climate zone. So heating and cooling loads are going to, well, heating loads are definitely going to factor in this one. And the way we push this information through is we log in to eTool through the plugin, which I've already done. And then we select our design, link it up, and then hit this update button, which pushes all the family types and quantities through to eTool. And we should see something going on over here now. Okay, we can see some impacts here, but I want to go in and verify that that import worked for me. Where are we? So the way the import works is that you've got two separate libraries, one in Revit and one in eTool, and we have to make sure that the libraries are talking to each other. And the way it sets up that linkage is that it remembers your previous matches. So you manually match the first time, and then it'll remember that whenever I have a slab edge element in Revit, it's going to match it up with this slab edge poured concrete element over here. And it looks like most of these things have been matched that are significant. I think most of these are cabinetry, etc., which are not significant at the building level. And this all looks pretty good. So we can now start analysing the model to understand where the impacts are. So what have we got here? Energy, recurring. This is your materials and construction equipment during the use phase for replacing items and repairing and maintaining, etc. Our initial products and our initial transport, and the embodied carbon of the water as well. And this is showing up because we're in Western Australia, which has a high penetration of desalination, which is quite carbon intensive when you have a pretty carbon intensive grid, which is what we have here as well in Western Australia. We can analyse this and drill down further. So if we look at a pie chart of the total impacts, these top two pieces of the pie are our integrated and non-integrated energy. And these bottom ones are the embodied impacts associated with materials here, transport of equipment and materials to site, the replacement over the life, end of life impacts, so there's transport off site and the disposal, the embodied impacts of the water. So you can see the embodied impacts of this building are actually nearly 50%, so pretty significant. But let's have a look at the energy in the water first and have a look at what's driving that. So this is a really holistic assessment. We're actually considering the plug loads, so the small equipment in the building as well, such as entertainment equipment, refrigeration, appliances, etc., dishwashers. But then what we've also got in here is our integrated loads, such as hot water, which is really high in this case. HVAC, quite high, but very small space to heat and cool, so not as high as what it would be in some dwellings. And then lighting down here, so we've assumed LED lighting, which is pretty much standard practice these days, and again, a small space, so not a lot of space to light, so relatively small impacts there as well. In terms of materials, we've got our clay bricks, number one in this case. Bricks are quite high embodied energy, good thermal mass, but high in embodied energy. The aluminium in the windows, in the framing of the windows, is quite high. We've actually got the impact of the refrigerants, which would be in two items in this building. One is the split system air conditioner, and the other one is the heat pump hot water system, is where we'd find these refrigerants. And We can drill down in here using this custom function to have a look at where these materials are, but for the purpose of the demo, I'm going to race through this. So we've also got concrete and cements and limes here, quite high impact. And then we've got carpets, so some of our finishes which recur over the life of the building. So not such a big initial impact, but certainly over the life of the building, these are going to add up. Some steel in here, so some of the reinforcing, but also the sheeting on the roof. So what I've done is, using this information and the adage, a problem well stated is a problem half solved, I've already penciled some strategies in about how I'm going to optimize this building. And we're going to do a range of, going to apply a range of strategies to the building. Some of them are going to be targeting operational energy, some of them materials, and some of them both. And so actually some water strategies here as well. So this first one, we're going to target a little bit of both. So we're going to have a look at what a super insulated fabric with low carbon materials could do to the performance of this building. So we're going to make that scenario active. I'm going to jump back into Revit here and show you that this is a live link, so we can push changes from our Revit file through to eTool LCD. And I'm going to choose a super insulated and quite thick timber wall here. Do the same for this top section of wall. And it looks like I've lost some of my view here, which I've got to work out how to bring back. Where are we? I'm not a Revit guru, so give me a moment. Here we go. And the other wall I need to change in this case is the internal wall, which is still brick at this point. So we'll change that for a timber wall, just so it's all timber construction. Okay, so I'm going to link this model up to my new design scenario that I created, the improved fabric design scenario, and then push those changes through. So I'm going to check that the matching worked. I'm guessing there's going to be some new components down here that need to be matched up. So I'll match those up. Oh, the other thing I need to do is change those windows out as well, which was part of my strategy. So I didn't model that in Revit, but I'll model it in here. I'll just select those existing windows and change them out with the new eTool template. And we'll go for timber frame. Double glazed, and I think there's one other, it is here. Okay. So we've made those two changes there. And the other thing we want to model, and we're just going to estimate this, is the thermal impact of those two changes. So normally we'd use thermal simulation software to measure this, but in this case we're going to assume a 25% reduction in both the heating and cooling loads for the purposes of the demonstration. And let's have a look at where we ended up. So a nice big initial change in embodied impacts, and that change increases over the life as you'd expect with energy savings. So altogether nearly a 12% reduction in impacts, which is actually really big for a single strategy. Quite often you're chipping away 2 and 3% at a time when you're optimising your model. So these big changes that reduce impacts in such a big fashion are really great. Note that any of these changes that I'm making in this demo, they're not prescriptive changes that you can apply to any residential building. This is really specific to this model. It's really specific to the characteristics, the location of this actual building. So, and that's one of the great things about LCA, is that it's going to highlight where those big impacts are for that specific use case. The next thing I'm going to model is a different way of tackling those heating and cooling loads. This time we're going to change the equipment that's delivering the heating and cooling loads. So we're going to assume that we're going to swap the split system air conditioner out, which is relying on electricity and fossil fuel, mainly fossil fuel electricity, and we're going to change it out with a wood pellet heater, which relies on timber, so biomass for heating, and ceiling fans for cooling, which has a lower energy requirement than the air conditioner, the split system. So the reason we can use the ceiling fans in this one is because it's in a colder climate and those cooling loads were really small. But what we'll do is we'll add our new equipment in first. And we'll compare it before we commit the change. Actually, have I made that active scenario? Yes, I have. Before we commit that change, we'll just compare the existing equipment, which is the split system air conditioner, with these new items, and you can see, yeah, these new items are definitely going to have a lower net impact. So we'll lock that in, and we can see here it's actually a little bit of an increase in the initial impacts, but over the life we get an improvement, and that would be a combination of reduced refrigerant impacts, because we don't have that those refrigerants in this new equipment, but also the reduced energy or reduced carbon anyway associated with these two, with the replaced equipment. So that's a win. We saw in the analysis that concrete was right up there as one of the biggest impacts. So we've got these two concrete items. Well, one here, which is so one concrete item here. Note, we've still got some refrigerants, and I'll talk about that in a minute, but concrete is our next biggest impact, so we're going to look at how we can reduce that. What we're going to do is run a scenario for geopolymer concrete, which is replacing the Portland cement with fly ash and a couple of other additives, which is much, much lower impact. So fly ash is basically a byproduct of coal-fired power, so pretty much zero impacts being a byproduct, and whereas clinker production releases emissions in its production and also requires a lot of heat. So we're going to use this bulk swap here to find that concrete, the concrete items. So we've got some concrete associated with, looks like the slab edge and the slab, probably the two main ones. And we're going to swap that out with a high fly ash concrete blend. We need to match the strength up, so it's a like-for-like swap. And we can see down here that it's about a 50% reduction in impact, so a real win there. There are some challenges associated with using fly ash, but we're assuming that we're going to be able to overcome that in this. Okay, now we're going to have a go at reducing some of the impacts associated with the finishes. So we saw here that carpet was really high, and it's moving up the list. It's still one of the highest impacts. Well, it's getting higher because we're eradicating some of the other highest impacts. And what we're going to do here is a classic elimination type strategy where we're going to remove the carpet and replace it with pretty much a zero finish. Well, it's not zero because there's a lot of equipment associated with grinding and polishing concrete, but not so much. So, yeah, very minimal materials. So what I'll do is go back into my import. I'm not going to edit my Revit model just to speed things up for the demo. I'm going to find my floor finishes here and just swap these out with a polished concrete floor finish. That's the one. Okay, a nice initial reduction in impacts, but really interestingly, a really big life cycle reduction due to that carpet, or the old floor finish being the carpet, being replaced over and over the life of the building, whereas this new floor finish is pretty resilient and doesn't need much maintenance and replacement. No replacement and not much maintenance. So I noticed in there when we were looking at the analysis that the refrigerants was still pretty high, and that's because there's still some refrigerants left in the hot water system. So maybe we can look at what we can do there. And hot water energy actually was pretty high as well. So that's obviously a target to have a look at what we can do with the hot water. So we'll pull this one up and we'll model this one next. So what we're going to do is put a really high efficiency hot water heat pump in, and we're going to spec one that has a low carbon refrigerant. Ironically, about the lowest carbon refrigerant is actually CO2 itself. It has the lowest global warming forcing effect of most of the refrigerants, but what we'll do is we'll do a similar thing here. We'll find our old hot water system, the existing hot water system. I'm going to add the new one in. Which is a heat pump, high efficiency with CO2 refrigerant. And that's going to reduce the energy demand, but also reduce the impacts associated with the refrigerant. And yeah, much lower impact, nearly half the impacts, which is great. So we'll stick with that. And another big reduction in impacts, really good to see. And then let's look at this one. So this is a different strategy. So still this time targeting materials. And it's the steel roof sheeting that we want to have a look at. I'm not sure why the windows are still here. I think I've forgotten to swap something out there, but we can have a look. So it's not our top remaining impact, but it's still pretty large, which is this the roof sheeting. We're going to see what we can do to reduce that. So one of the things we can do is look at product quality. So In this case, we're going to run a scenario where we spec a high quality roof sheeting that is going to last longer than a run-of-the-mill one. I must say, run-of-the-mill is pretty common in Australia. Sorry, high quality is pretty common in Australia, but we are getting more penetration of lower quality roof sheeting in. So this is just specifying the better quality option. So again, I'm just going to find my roof template in here, and I could do a direct swap, but I think I've got a template for the high warranty roof. Oops. So timber frame, 10-degree pitch, that's about right. So what this is doing is going to reduce the replacement of the roof. I think there was only one replacement of the roof earlier in the original model, but this one is going to reduce that further. Yeah, so no change in the impacts on day one, but a reduction in impacts over the life. So a modest reduction, nearly 1%, which is as I said, that's still something that you want to try and target. Yeah, and pretty easy to affect that as well. Most people are probably going to want a high quality roof sheet anyway, so it should be a win-win. What we're left with here is some pretty high energy and water impacts. A lot of this is in the plug loads, and there's not a lot a designer can do to really reduce that. But one thing you can do is help the occupants understand where their energy use is with energy monitoring. And in particular, if you give them real-time feedback and compare their energy use to best practice, then you should get, well, scientifically, when these units are installed, randomly in buildings, we see about a 15% drop in energy use when you've got that comparative feedback. So we're going to simulate that. There's a small amount of additional impacts, I guess, or equipment in the building for this. So we will model that. And then we can either go in and bulk swap our energy and reduce it by 15%, but there's this other feature in eTool LCD which enables us to just adjust the energy down over here. So we'll run that. And we're seeing a slight, tiny increase in impacts on day one, and then a big saving over the life. So yeah, really big saving, nearly 8%, which is good. The next one we'll look at is water efficient fixtures and fittings. So we saw in here with our energy and water impacts that water was, it's actually really high now. It's the third biggest impact, so it's really pushing up there. So what we'll do is we'll spec some just energy efficient toilets, showers, etc. And that's going to have a few effects. So let's find my starting point here. So it's going to reduce water demand. It's also going to reduce water treatment. It's also going to reduce energy associated with the hot water as well. So we'll try and simulate both of those. So I'm going to select all of this energy. This pool, I think this is 0 anyway. We've zeroed that out. It won't affect if we have any outdoor water. So the garden, I think this is zeroed as well anyway, but we'll just deselect those. But all these other energy items apart from the outdoor water use will be affected. So we'll reduce this. Let's say we can, and this is pretty reasonable. I think if you go for the highest Wells rating for all your fixtures and fittings, you could probably achieve a 50% saving, but let's just assume a more modest 30% saving in energy, so 70% of the original. In terms of additional material, you're probably not seeing a lot of additional material. The other one we want to change there is the loads associated with the hot water. So here we go. And I'm just going to multiply this whole thing here. 0.7. Well, it's probably not the whole lot. Well, in this case, it would be a lot of it, but there are other hot water uses, so let's just reduce that by 0.8. I won't go into details of how that works, but what we're trying to do is demonstrate more how to optimize. So we've made a change there to both the water and the energy associated with those water fixtures and fittings, and we can see there's a really big improvement in impacts, and there might be some slight change at the start of life, but I don't think it would be significant. All our water fixtures and fittings nowadays need to have some kind of flow restriction or so this is just changing that a little bit in terms of how it operates. So the last thing I'll do is just run a renewable energy strategy to see if we can sort of reduce this down to 0 and maybe even pump a little bit of energy back into the grid and offset the remaining energy as well. So I think where we started was around about 275 or something like that, I think, from memory. So we've nearly halved our impacts already with the scenarios that we've applied, which looks about right. So we're really heading in the right direction. And now we'll add a renewable energy system, a solar system, to see if we can knock it all the way down to 0. So just adding this strategy to document that. And then pretty simple to model this one. And we'll go for a modest size system, maybe 3 kilowatts perhaps. And we're still a little bit of impacts there. So maybe if we change that to a 3.5 kilowatt system, we might get down to net 0 carbon, which would be pretty cool. Yep. So that's how to optimize a building, and using a little bit of BIM integration as well as a demo there. The reason we've got net 0 carbon is because we're actually generating more electricity than we're using, and we're getting a credit for feeding that back into the grid and offsetting somebody else's or reducing somebody else's reliance on fossil fuel electricity. So good result.